Good day, everybody. Thanks for joining me for this presentation on the KNX Energy Management with KNX Classic and realization of the EN50491-12-2. Let's have a look at the agenda I have in store for you. First of all, I will take a glance at energy management. First, we ask ourselves the question, energy management, is that a thing that is that an application that KNX can handle? Of course, the answer is yes, we can do that already. I will explain you the philosophy behind the prEN50491-12-2 standard. Then next thing, I will answer the question, what kind of energy management functions could be realized with prEN50491-12-2. I will explain you the 5 different so-called control functions that exist in this standard. I will inform you about the fact that KNX is currently designing functional blocks for the realization of this standard even on KNX Classic. And I will explain you with some of the functions that are contained in the so-called fill rate based control function. I will explain some of the functions, how we will realize that with newly designed KNX data point types. And I will round off with how will this all work together, KNX Classic and potentially KNX IoT devices, how will this work together at all. Okay, let's get started. If we look at how KNX realizes energy management, we can already confirm that already today KNX is capable of covering a lot of applications within the energy management domain. Be it sub-metering, be it peak shaving, load management, battery storage, inclusion of solar panels, inclusion of e-car, doing smart metering, of course, ventilation, air conditioning, etc., and heating have been around for quite some years. Heat pumps can be integrated into KNX, and boiler control and individual room control has also been nearly there from day one. But if you look how this kind of energy management is realized, then this is mostly at device level, and this is mostly done, or this can be done in a visualization software or in a central panel unit that also supports advanced logic operations, or in a separate home or building server, like you see one over here, some examples you see over here, and or in a combination of all of this material. Of course, as is accustomed in KNX, normally these devices are interlinked thanks to the help of a competent, skilled KNX partner, and this data can also be made accessible via the internet, via appropriate apps. Of course, the products I show here in these slides are only possible solutions. There could be, of course, others available. What is actually the vision of the prEN50491-12-2? Because of the PR. The PR means project EN. That means that this EN is not yet available as a final standard, but it is expected to be available by at the latest end of this year. The architecture of the whole application is actually already laid down in the EN50491-12-1. This is already a standard since July 2018. And the whole concept builds on the idea of having a customer energy manager, one or multiple. This standard version foresees one customer energy manager and a number of resource managers. These resource managers abstract the home and building electronics system towards the SEM as regards the energy need or the energy offer. Well, that means that actually the SEM only looks at the energy management functionality which is provided by the resource manager. So the device could have other functionality than just the resource manager, but the resource manager is there to inform about the product's flexibility as regards energy supply or energy need. This resource manager could be a single device, it could be a bundle of devices, it could even be an entire system. And the 50491-12-2 lays down this so-called S2 interface. This S2 interface is the interaction between the SEM and one or more resource managers, but the standard does not lay down which protocol must be used for that. You can use any type of protocol to exchange the data that is laid down for the S2 interface. The S1 interface, which is the connection of the customer energy manager with the grid, this is out of scope because this is handled by another technical committee. This is the IEC TC 57. I always compare the architecture with sort of an orchestra, where the SEM is the director of the orchestra, and the resource manager are the different musicians. So in order to make the best of the available energy supply or the energy need, this director makes sure that this orchestra of resource managers plays the right tune. And this does not end up in a thing that is no longer detected as a song. Okay, so the EN50491-12-2 defines different control strategies. And these control strategies are intended for different types of possible different types of energy management devices and interactions between a resource manager and a SEM. There are 5 different control strategies defined, and they are called control types. The first control type is the so-called power envelope-based control. I always compare this control type to a sort of a speed limit. The SEM will ask the resource manager to stay within certain minimum and maximum limits with its power. And these limits can change over time, as you can see in this graph. For instance, the SEM could ask a heat pump to produce less energy. The resource manager will also send a power forecast, and the SEM will consequently adjust the power envelope to the power forecast that was given by the resource manager. So this could be either a single value, meaning this is the minimum or maximum, or it could also be a range. So the min-max could be a range or a single value. And the resource manager, the device, must react accordingly on the updated power forecast. The second control type is the so-called power profile-based control. The power profile-based control is a control strategy that is ideal for instance, such devices as white goods. The device tells when it wants to start and when it needs to be ready. So it tells, okay, I want to start at 5 o'clock, but I need to be ready by 9 o'clock in the evening. The device will inform about the different phases of its entire process it needs to go through, the different phases of a washing program, for instance. And it tells this to the SEM by means of power sequence containers. And inside these containers, the device will provide a number of options as power sequences. So the device actually tells the SEM, these are the options you can choose from. And there is also the possibility in a container or in a power sequence that it can be delayed. However, it can only be delayed for a maximum indicated time. So you cannot delay it much longer than that. And also the power sequence tells whether you can interrupt the power sequence, yes or no. For instance, during a washing program, there are phases that are not interruptible, which you need to finish before continuing with the next power sequence, which could be interruptible. Okay, the third option or the third control strategy is the so-called operation mode-based control. This is typically for devices that assume a range of power levels modeled as a state machine. So I have made a comparison to a state machine. For instance, a device could be in the off state. It could be running at reduced power, or it could be running at full throttle. And between these different operation modes, there could be transitions. And these transitions could be restricted by so-called start timers or blocking timers, meaning you cannot start before, and it must at least run this time. The operation mode-based control resource managers can give exact values for the power levels, but they can also give ranges. And in this way, the devices actually, or the resource managers, describe their possibilities towards the SAM. And the SAM can in this way make realistic plans for the future. So it knows the possibilities of the devices. So it knows how some devices could be switched on or switched off to save energy or to consume energy when there is abundant energy. So the SAM will send to the resource managers the targeted operation mode. So I want you to go to the operation mode with the ID 2, and you should do that in the indicated time. Okay, the fourth control type is the so-called demand-driven based control. This is ideal for devices that are flexible in the type of energy they use, but for those that are unable to store or buffer energy. Meaning, you could, for instance, have a device or a hybrid heat pump that can work on electricity or gas. For working on electricity or gas, the device is linked to a specific actuator. And these actuators will then supply their different actuator descriptions. So each actuator has a specific state machine again, which contains a number of modes and again a number of transitions. And these transitions are again influenced by blocking timers or starting timers. So the device will inform about the demand rate. This can again be a single value or a range. The device can also provide a forecast of the average demand rate in the near future, so that the SAM can also again plan the energy management better. And the operation mode of the actuators will indicate how much can be produced in that particular mode. So the SAM must find the appropriate combination of the different operation modes of the different actuators to fulfill a certain demand rate. And last but not least, and for this particular control mode, I will also explain you how we want to realize that with KNX Classic, is the so-called fill rate based control. This fill rate based control is ideally suited for devices that can store or buffer energy. So the device informs on how full it is, and it can inform on the minimum and maximum values that may never be exceeded. So you may never go beyond 15% of the storage and or maximum 85% of the storage. The device may also inform about the time when it wants to be full. It could say, I want to be, for instance, an electric car, could say, yeah, I really need the car to be ready by 7 o'clock in the morning because I want to drive to work. And one of or more actuators, again, a bit the same as the previous control type, one or more actuators, which you can see here, may influence how full the storage is. So the actuators are again modeled in the same way as is done for the previous control mode, the operation mode control. So they need to indicate what effect they have on the fill level. So on the basis of this information, the SAM will again send instructions to the device indicating the desired running mode for the actuator and the desired time of the transition. Also, as you can see, the device may also model its leakage behavior. For instance, a boiler tank in which you store hot water. Of course, the temperature may decrease over time. So this storage tank should maybe also inform the SAM about this effect. Okay, so I had promised you to round off this presentation by telling you how this standard could be realized. So the energy flexibility management could be realized by means of KNX. So during the exercise of doing this at KNX Brussels, we have looked at the different possibilities that could solve this exercise. As you may have heard from my presentation, many of these data structures are mostly device parameters, and they do not change too frequently. But we don't want, of course, an installer to again and again come to an installation to change these parameters. This is simply not possible. So we would need some form of communication allowing to change these device parameters. Mostly, as you may also have heard, this is a one-to-one communication. So it's one resource manager talking to a SAM or a SAM to a resource manager, but you don't have any resource manager to resource manager communication or one-to-many communication. So if it's a one-to-one communication, you could contemplate making the communication based on interface objects and properties. But this is not really an option because there is no support for configuration of such devices in the current ETS. And you could also think of, okay, maybe communication would be better with KNX IoT. But for some of the options, you would need Point API, and Point API IoT is still under development, so it's not yet there. So it was decided to still design the KNX functional blocks for these structures using classic group communication. The newly defined DPTs are mostly of a variable length. And of course, in standard group communication where you use 14 bytes, you have seen the data structures before. In the control types, it will not be possible to use, of course, normal 14-byte group communication. You will need to use extended group messages. This extended group messages up to 250 bytes of payload will be supported in the ETS 6. And of course, as soon as the Point API becomes available, also these structures could, and more elaborate structures, could also be sent via the Point API with JSON or CBOR encoding. So let's look at a couple of these data point types that we have newly designed. For instance, the fill rate based control needs to inform about the state machine. So the resource manager needs to use this data point to communicate about the state machines of the connected actuators. Well, the whole structure, which is of variable length, starts off with a 2-byte information containing actuator metadata. This informs about which commodity this actuator supports. Is it electricity? Is it gas? Or is it oil? And/or oil? How many operation modes does this device have? Here in this practical example, there are 3 operation modes. There are a number of reserved bits, and also you want to inform about how many transitions there are between the different operation modes. Here you can see in this particular example, there are 6 transitions. And after that, there are the different operation modes are communicated. And after that, in the same data point, the several transitions are communicated. The operation modes will have 10 bytes each, and the transitions will have 6 bytes each. I will now explain you how the several operation modes will be modeled. In the operation mode, we start off again with metadata on the operation mode, in which it is communicated how many of the elements is communicated in the for the operation mode. Of course, every operation mode in the message needs to have an own ID. Then it is informed which commodity quantity is modeled by this operation mode. Is it electrical power of single phase, or is it electrical power of a 3-phase actuator? Is it natural gas flow rate? Is it heat flow rate? Is it heat thermal power, or is it oil flow rate? So this byte indicates one of these. And then the different elements actually model this kind of table. The table which informs on how fast the actuator can fill the storage, because the rate is mostly depending on how full the storage is. So, for instance, between 40 and so when the storage is 15 to 35% full, the fill rate in watts, in this particular case, watts per second, is 0.001 when you insert 40 watts, and the fill rate is 0.55 when you insert 2500 watts. And to model this table, we communicate a fill level range of 2 bytes with an upper level and a lower level, exactly this. We use 2 bytes of filling rate, which is actually this figure. And we indicate the power range, so exactly these values, as F16 KNX float. And then we move on to the transitions. I will now explain you how the transitions are modeled. This is a little bit more simple. It is, first of all, there's a byte that indicates whether this is only a transition that applies when it's an abnormal condition. Of course, there is a transition ID communicated. Then in 1 byte, we communicate the transition, that this is a transition between operation mode X and operation mode Y. We indicate which start timers apply to this, and we indicate what blocking timers apply to this. And by the way, we have decided not to communicate each time the exact timing value. No, instead of that, we have designed a separate timer status that informs about the number of elements. And then for each timer foresees 11 bytes of data. 1 byte indicating whether the timer is running or the timer is valid, and the ID of the timer. Then the timer duration in seconds, and the finish timestamp modeled as DPT date time. And to round off, of course, we also need to define the start timers and the blocking timers. The actuator needs to inform about the different timers, and here it informs which timers are exactly, which start timers are exactly active. And here it informs about which timers, I have to correct myself, which timer is a blocking timer and which timer is a start timer. Okay, how could the communication now work? The communication could, of course, when some energy actuator, where is it? Yes, this energy actuator wants to communicate momentary values, it can continue to do so in the short group messages in 14 bytes, like the devices exist today. But this battery storage could inform on these EN50491-12-2 messages with the extended group messages. So actually, the arrow should be communicating, of course, towards the SEM. Or it could, in the future, it could communicate such data structures, also making use of more elaborate JSON data structures to communicate this information to the SEM. So today you could use extended group messages, and tomorrow you could use the point API communication. Many thanks for joining me in this presentation. I hope the information was useful, and should you have any questions whatsoever, I'm more than happy to answer them. If not, you can always send me your questions also via email to joost.vermerest@knx.org. Many thanks and have a nice day. Bye-bye.